So in this video, we're going to explore one other piece of functionality, ethers in general, and then epoxides, which are cyclic ethers. They're a special kind of cyclic ether, a three-membered ring containing an oxygen. So in general, an ether has the form of R, so rest of molecule, right? O, and then R. Or that's if you have a perfectly symmetrical ether, right? You can have these R groups be different things. And we indicate that with just a little prime when R is different. So notice that unlike an alcohol where you have ROH, in an ether, we have an oxygen atom that is flanked by two R groups. It is not, the oxygen is not directly connected to a hydrogen. And so ethers cannot hydrogen bond with themselves. And that actually affects their physical properties. So they have dipole-dipole interactions, they have dispersion forces, but they cannot hydrogen bond with themselves. And so as a result, we end up noticing that ethers, compared to alcohols of comparable mass, have much lower boiling points. And their behavior is a little bit different. Let's start out by naming them, and then we'll get into the reactions. So the nomenclature for ethers, we've got the IUPAC system, in which we're going to take the alkane and name the ether as an alkane with an alkoxy substituent, an RO substituent. The substituents are going to be named by replacing the YL ending of the alkyl substituent with oxy. So in other words, we could take a methyl group with an oxygen attached. If this was bonded to R, right, rest of molecule, so that would make it an ether, then this would end up being, instead of methyl, it would be methoxy. So this is IUPAC nomenclature. We'll explain common in a sec. Another example, this would have been an ethyl group, right? So that little line right there after the O is saying I'm going to be bonded to another R group. And this is ethoxy. So in other words, these can be substituents, right? So for example, if we had something like this, we're going to find our longest continuous chain of carbons, just like you would name a regular alkane, that contains the functionality, right? So the longest continuous chain of carbons that contains the functionality is going to be 4. So 4 carbons. And we're going to give priority, in other words, the lowest number, to the functional group. So the ether is going to take priority. So we're going to start numbering in this direction, 1, 2, 3, 4, which means that with IUPAC nomenclature, the methoxy group, so this right here, ends up being in the methoxy group, is on carbon 2. And so we have 2 methoxy butane. So this is the systematic way of naming an ether. Common nomenclature, which is for smaller ones especially, typically used. You're literally just going to take the names of both of the alkyl substituents and put them in alphabetical order and follow it up with the word ether. Much easier, especially for smaller ethers. So you could have something like this. So here we have two alkyl substituents. We have a methyl group and we have an ethyl group. Eth comes before meth, right? So we have ethyl, and this is going to be separate words. Ethyl, methyl, ether. If we were using IUPAC nomenclature for this, instead of ethyl, methyl, ether, we would find the longest continuous chain of carbons, right? So I'll put a C after this. This is going to be our common nomenclature. If we want to do IUPAC for this little molecule, we find our longest continuous chain of carbons, and that's 2, right? That contains the functionality, and that functionality would be the methoxy group, right? So this, and you don't really have to put a number on this one because it's so small. Either carbon would be carbon 1. So this would be methoxy ethane if you were using IUPAC nomenclature. So ethers are pretty easy to name. They are generally pretty sturdy. So oftentimes we'll actually protect an alcohol, chemically protect it. So in other words, disguise it as an ether. If we want to take a molecule through a synthesis and there are multiple functional groups and we're choosing to not react the alcohol portion, right? When we're, say, reacting the aldehyde portion or whatever. So very often we'll disguise these as the alcohols as ethers because they're pretty sturdy. The alkoxy group of the ether and the hydroxyl group of the alcohol are nearly the same in terms of their basicity, right? Their conjugate acids of the conjugate acids of those two groups have similar pKa's, in other words. So both groups are strong bases, right? So the reactions that we did with alcohols are similar to reactions. Some of them are similar to reactions we can do with ethers, but since both of those groups are poor leaving groups because they're such strong bases, RO minus and OH minus, we need to protonate ethers just like we do alcohols in order to get them to react, because we want to create a better leaving group, right? A weak base. So reactivity. For the ethers, we're going to compare an alcohol, so ROH versus ROR. So the leaving group would be, in each case, OH minus and OR minus, right? Leaving group is hydroxide. Leaving group would be alkoxide, right? Whatever the alkyl group is, followed by oxide, right? So that's your leaving group. So these are strong bases. So therefore, they are poor leaving groups. So we must protonate first to create a good leaving group. In other words, if we were to protonate the hydroxide anion, you'd get water. That's a weak base. And if you were to protonate the alkoxide anion, you would have an alcohol, also a weak base. Both of those are decent leaving groups. And so in order to react ethers, just like we do with alcohols, we have to protonate them first. And you need a really strong acid too. So we refer to this as activating the ether. So the ethers can undergo nucleophilic substitution reactions, but if you're using a really strong acid, they're pretty hardy, right? So HBr, HI, right, hydrobromic acid, hydroiodic acid are usually the acids you see, and almost always you'll see heat involved. So it's pretty harsh reaction conditions. You need to crack an ether. That makes them nice and hardy. And they're a little sturdier than alcohols. So we, again, sometimes use the ether functionality to disguise an alcohol in other syntheses. So in general, for the ether, we could take R, and I'll just let this be asymmetrical so that we can follow the leaving group along. This right here is your pore leaving group. So what we'll do is we'll allow it to react with a strong acid and we'll protonate the ether This is a good leaving, this is a good leaving group, just an alcohol, right? A neutral molecule. And with heat, and of course your leftover I minus, which can be your nucleophile, you can create an alkyl halide and an alcohol. We call this cleaving an ether. So you protonate the oxygen on the ether. What happens after the ether is protonated kind of depends on the structure of the ether, right? If the departure of the alcohol creates a relatively stable carbocation, like if you can get a tertiary carbocation, then the alcohol group will just take off. In other words, you'll have an SN1 reaction happen. So what am I talking about? We'll do substitution reactions. So if I can start out with a tertiary carbon, so the ether looks like maybe something like this, right? So you have your tertiary carbon, and I allow this to react with a strong acid. Then the lone pairs of electrons on the oxygen are going to attack the hydrogen on the acid, dump electrons onto the halide, and I'm going to create my good leaving group. Just like with an alcohol, we're setting this up for success. Why is methoxide not just going to leave on its own? Because it's too strong of a base. Remember, strong bases make terrible leaving groups because they're more reactive when they leave, right? The strong base is more reactive, it's unstable, it's higher in energy, that kind of thing. And then this takes off, right? Water is going to, or in this case, your alcohol is going to take off, and you're going to form a carbocation. So this right here is going to leave. And your nucleophile, so here's your carbocation, your nucleophile can come in. And your fast step is the formation of the alkyl halide. So in this case, we have an SN1 process, right? So this is SN1, because we have formed a stable carbocation. Your leaving group took off, you formed a stable carbocation, and then the nucleophile came in and attacked. If the departure of the alcohol is going to create an unstable carbocation, so like a methyl carbocation, which is wildly reactive, or a primary carbocation, then the alcohol group's not going to just take off and create that unstable carbocation. It's going to have to be displaced by the halide ion, right? Your nucleophile. So in other words, an SN2 reaction would occur. So if I have something like this, and I'm going to put this up here to save space. So I'm going to come in and I'm going to protonate my ether. The halide's going to take off. So in this situation, if I were to lose the alcohol, then I would end up with either a primary carbocation, right? So if methanol took off, I would have a primary carbocation. If propanol took off, I would have a methyl carbocation, which is pretty reactive, right? So in this case, the iodine, or iodide, I should say, is going to come in. And I'm going to attack the backside of the less sterically hindered carbon. So why did I pick that carbon instead of the methylene to the right of the oxygen? Because it's less sterically hindered, right? The methylene to the right of the oxygen is flanked by the oxygen with all its stuff going on, and then an ethyl group. But the carbon on the left side of the oxygen has the, oxygen and all that stuff going on the right, but then just hydrogens, right? So that's the reason I chose that carbon. And then this is going to take off. So this is SN2. And I end up with methyl iodide plus N-propanol. And this proceeded through an SN2 mechanistic pathway. So these are not exactly, the most interesting molecules. They are usually used as protecting groups for alcohols or other, reactive compounds you can turn into an ether. One thing we do take advantage of, though, is because they're so stable, they're not very reactive, and because they can the oxygen has a lone pair of electrons that we can use to solvate other organic compounds. They make really good solvents. So ethers are often used as solvents. I just want to share with you a few examples of pretty common solvents that are ethers. So one that you're probably familiar with, when someone just says the word ether, they're like, I'm just going to use ether. They're usually talking about diethyl ether. So that looks like this. Kind of looks like a little bat. So we have diethyl ether. Another one that's really commonly used in the lab is tetrahydrofuran. So THF, in other words. A furan ring, so we have a cyclic ether there. They have common names. Diethyl ether is usually affectionately termed just ether. We've got, you may have heard of 1,4-dioxane. I don't know what your experience is with ethers as solvents, but dioxane, most people have heard of it at least. This is 1,4-dioxane. What else can you think of? Oh, MTBE. So they used to put this in gasoline. So this methyl tert butyl ether. MTBE. I think now they just use ethanol as a source of oxygen, but that's a pretty sweet little solvent. It's nice and hardy. It's got a good mass to it. So if you're the person in the lab doing, the chemistry, you want an ether to solvate your stuff, and you don't obviously want your solvent to participate, or if I should say, you don't want your solvent to participate in the reaction, and you need an organic solvent to help dissolve your stuff. And you're not hoping for an ether that is going to blow away in the breeze like diethyl ether. It's got a really low boiling point. MTBE is nice and sturdy. It's got a decent amount of mass to it. So it's a pretty sweet solvent. There is a reaction that, sorry for the sirens coming here. There is a reaction that is sort of a named reaction that uses ethers very strategically as a solvent. It's called a Grignard reaction. So a Grignard reaction, very specifically, is an organometallic reaction. So it involves the use of an organomagnesium compound that has to be created by you. And it is extremely sensitive to any whiff of a proton, water in the atmosphere, water in the solvent, water hiding in the glass that you're using, the vessel, like the flask that you're using. So you usually have to flame dry the flask, let it cool, add the ether. Don't flame dry the ether, whatever you do. And make sure everything's super dry, because otherwise you'll kill the Grignard reagent. Very specifically, though, a Grignard reaction involves the use of the metal magnesium. So we have other organometallic coupling reactions, is what we call these. We're going to create a new carbon-carbon bond. But in order to be officially a Grignard reaction, you need to use magnesium, because Grignard was the dude who actually did this chemistry. Magnesium was the metal he used. Ether was the solvent that he employed, and I want to show you why. So in general, a Grignard reaction will take an alkyl halide. So we'll just say Rx. So this right here can be our alkyl halide. So usually X is our little slang symbol for a halide, right? And we're going to allow this to react with solid magnesium. So magnesium turnings or magnesium shavings or something. And we're going to allow this to react in anhydrous ether. Diethyl ether is often written like that, ET2O. ET is the abbreviation for ethyl. You could do it in THF, any one of these solvents, right? But diethyl ether is pretty cheap, right? Easy to come by. And anhydrous, by the way, needs to be dry. And I say that because you might be wondering, so in other words, anhydrous, like why would you have water in your ether? Some solvents will attract water molecules. So anhydrous means without water. Some solvents can share similar intermolecular forces with water, and any water in the atmosphere will be attracted to the solvent. And ethers are particularly hygroscopic. So very often you'll find a certain percentage of water hanging out in the ether. So you will specifically buy a bottle, and it will be more expensive, of anhydrous ether. And it doesn't have any water in it, and that's what you'll use for your Grignard reaction, because you cannot flame dry your ether unless you want a fireball, which can be kind of fun. What happens is you're going to allow the magnesium, or the magnesium will coordinate with the alkyl group by inserting itself between the carbon that bears the halogen and the halogen, right? So the magnesium is going to just sit itself between the carbon and the halide. And this right here is your Grignard reagent. We often abbreviate reagent, just RGT. This thing right here is going to behave like your alkyl group with a lone pair of electrons and a negative charge. It is a wicked little base, a really reactive species. Any hint of a proton, this is why your solvent needs to be super dry, any hint of a proton, and you will just protonate whatever your alkyl group is, and that's the end of your Grignard reagent. So you want to make sure everything is super dry. Let's show a specific example for this reaction. Usually, when we have the organic students do, if you do a Grignard reaction in lab, it's usually bromobenzene plus magnesium in dry ether. So see how we've written this, instead of plus Mg, we put the Mg on top of the arrow. I'm trying to show you different ways that you could be presented with looking at a reaction equation. What you'll get is the magnesium inserting itself between the carbon that bears the halogen, the bromine there, and then the bromine will be bonded to the magnesium. This is going to act like benzene with a lone pair of electrons up the top there. So basically a heat-seeking missile for an electrophile or a proton, right? So after this is done, you can take your Grignard reagent. So we'll take this down here, which behaves like, again, a carbanion. And you can allow it to react with, say, an alkyl halide. And it's a great way to create a new carbon-carbon bond, because your aromatic ring is going to act like a carbanion. It'll be your nucleophile, and you're going to form a bond between the carbon that had the magnesium coordinated with it and the electrophilic portion of your alkyl halide. So you'll form a bond between that carbon and that carbon. There's another type of ether, it's kind of special, that is a little more reactive, and I'm going to show you a Grignard example, and there'll be a nice segue into this special kind of ether. I could take my alkyl halide, and I'm going to first allow it to react. I'm going to show you another way that we can present a reaction equation. Instead of showing them in separate steps like I just did at the top there, I'm going to put them stepwise over one arrow and just give you the product, right? So this is going to be magnesium, and then we put a little comma, and there's the solvent. And the second step, after you have created your Grignard reagent is we're going to add our electrophile. In this case, I'm going to go ahead and I'm going to use an ether, not as the solvent, but as a reactant. And it's going to be a special kind of ether. It's a 3-membered ring that contains an oxygen. So we're going to do a little section on this next. This is called an epoxide. The ring strain associated with an epoxide is so significant that often you don't need to protonate the oxygen in order to get it to react, because attacking one of those carbons will release electron density up to the oxygen and alleviate the ring strain. So they're like pretty sweet little electrophiles. The third step, and this has to be done after you have attacked the epoxide, is we're just going to add some acid. Sometimes you'll see an acid workup written, or sometimes you'll see H3O. Workup is like if you're in the lab and they ask you to do an extraction or something like that, but they ask you to pour your product into the separatory funnel and then add like, you know, a base or an acid to the flask, and then you shake and vent kind of thing. That's the workup, right? In that step, chemistry is actually happening. And then you're going to be either protonating or deprotonating your product to encourage it to go into one layer over the other so you can separate it, right? At the end of all of this, what you're going to get is an alcohol. Did I add too many carbons? Let's see what we got. We're going to form a bond between that carbon, and these are the same, so that carbon. So there's 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. And this will be bonded to the oxygen. The acid is there to protonate the oxygen after we crack the ring open. So I'm going to show you how a reaction like this could happen in the next sort of like section when we cover epoxides. So we're going to create the Grignard reagent. Grignard reagent is going to behave like this. So your Grignard reagent will have that carbon coordinated with the magnesium, which will have bromine on the other side, right? But it's going to behave like this, and then it's going to attack the epoxide. So this is going to come in and it's going to attack that carbon. We're going to dump electron density onto the oxygen. And this is the step where you protonate. You have to really make sure, though, that you're ready to, you have to make sure that this reaction is good to go before you add the acid, because you will kill any unreacted Grignard reagent if you put water or any whiff of a proton anywhere near that thing before it's done. So let's talk about that little fancy cyclic ether, that little 3-membered ring. So there are, in the lecture notes, I've shown how we can synthesize these. You can also, and they're easy to make, right, in the lab from alkenes and peroxy acids. So an epoxide is going to be an ether, but it's a special kind of an ether. It'll be an ether in which the oxygen is part of a 3-membered ring. And they don't all have to just look like the one we just used. They can have groups hanging off the carbons. That's okay. The common name, so we have nomenclature for these. The common name of an epoxide is just obtained by adding oxide to the common name of the corresponding alkene. So for example, I could take ethylene. So we're talking common nomenclature. Instead of ethene, it's ethylene. So we'll write that over here. This is common nomenclature. If I create an epoxide out of this, I'm going to make the three-membered ring. And it will be named ethylene oxide. Two words. Right, so we'll do another example. We could take propylene. Remember, this is common nomenclature. That would be propene if it was IUPAC, but it's propylene because it's common. Remember, we name the alkyl group, and then we stick the suffix for the functionality on the end. This would be propylene oxide. So, of course, IUPAC nomenclature is going to be a little bit different. So, another way that we could name these is we can take the epoxide and name it as an alkane, with the epoxide portion being sort of like its own special substituent, even though it's not really, it's a part of the whole thing. We're going to call it an epoxy. You've heard of epoxy before, right? So we can name the epoxide by naming the alkane, and then we're going to use an epoxy prefix that identifies the carbons to which the oxygen is attached. So for example, I could have this molecule where I find my longest continuous chain of carbons like I normally would for an alkane. And then I'm going to use the prefix epoxy, but I'm going to tell you what carbons the epoxide is actually a part of, right? And you're going to give priority to the ring, just like you would any other piece of functionality. So in other words, I'm going to number this from left to right because it puts the lowest number on the epoxy group. So this ends up being 1, 2 epoxy butane. Another example we could do is, why don't we do something a little fancier here? Put some more substituents on here. Okay, so now what do? Well, you find your longest continuous chain like you normally would, right? So that's going to be 3 carbons. One of those methyls is going to be a substituent, and the epoxy group is going to be a substituent, but it'll be sort of the star of the show. It's the functionality, right? So we're going to give that priority. We're going to use the prefix epoxy, and we're going to give it the lowest carbons. That will end up putting the methyl group on carbon 2. And we're just going to list them in alphabetical order like we normally would. So 1, 2, epoxy. And then you got to tell somebody that this carbon, or I'm sorry, this methyl is on carbon 2. And in all one word, it'll be propane. That was your longest continuous chain, was 3 carbons. So we can make these things, these epoxides, again, out of an alkene and a peroxy acid. So what you'll do is you'll take a peroxy acid, and a peroxy acid, by the way, is a carboxylic acid, I'll just use R, where you've got 3 oxygens, 2 of them are connected to each other. This is a peroxy acid. So it's a carboxylic acid, right? R is just rest of molecule, and it has an extra oxygen atom. And it's that extra oxygen atom that's going to be transferred to the alkene in order to form the epoxide. So the reaction is going to increase the number of carbon-oxygen bonds in the reactant, and so therefore it is an oxidation reaction. So we're going to allow this to react with an alkene. So just generically, we could say R, and then just put a double bond here. We're going to turn that into our epoxide. So here we have an alkene. And we have a peroxy acid, and here it's going to be the pi bond because it's weaker that's involved. So the pi bond will break and the epoxide is formed. The leftovers are just going to be the carboxylic acid minus 1 oxygen. So that will be your byproduct. So here you get your epoxide. And this is just your carboxylic acid. So we can react these just like we can any other ether. These are going to be more reactive, right, because of the ring strain. So there's 2 ways under which these can undergo substitution reactions with hydrogen halides. So just like you would any other ether, we're going to use HBr or HI or whatever. The mechanism of the reaction kind of depends on whether or not it's carried out in acidic or basic conditions, or I should say acidic or neutral or basic conditions. So neutral and basic conditions are one category, acidic conditions are another category. So under acidic conditions, you're going to protonate the oxygen of the epoxide. So let's do substitution reactions with these. We'll do acidic conditions. And I separate these because it matters which carbon gets attacked. Not the same carbon will get attacked under acidic conditions as neutral or basic. So that will affect, the regiochemistry of the alcohol that's formed. Okay, so let's start out with acidic conditions. under acidic conditions, we are going to protonate, and I'll just use ethylene oxide or oxirane is another. There's a few different ways that we can name this, and we'll find this with amines too. There's like a few different names that we can give these. We'll start off with just a simple epoxide, and we're going to use the lone pairs of electrons on the oxygen to protonate the oxygen. I'm going to attack that acidic hydrogen, dump electrons onto the bromine to create bromide. So then, if this wasn't reactive before, it is really reactive now. We don't have to protonate these to get them to react. Because of the ring strain, they're already pretty reactive, right? So bromide can come in. And it's going to attack one of the carbons. In this case, they're both the same, so it doesn't matter. And very quickly, you end up with your alcohol. And the bromine attached at the other end. So under acidic conditions, the acid will protonate the oxygen of the epoxide. That's that first step. The protonated epoxide is going to undergo a backside attack by the halide ion. So this is SN2. Well, in this case, SN2. I'm going to explain in a second how it's kind of like SN2, SN1-ish when I draw an asymmetric epoxide. But we're going to do a backside attack on the by the halide ion. This thing is going to happen at room temperature. We don't have to heat this up like a regular ether with a hydrogen halide. And because this epoxide was so reactive in the first place, protonating it only makes it more reactive. So you can actually crack these open with really poor nucleophiles. So this was where I was kind of like going with it's not quite SN2, not quite SN1. If you have different substituents attached to the two carbons on the epoxide, then the major product is going to be the one resulting from the nucleophilic attack on the more substituted carbon. So what I'm referring to as being not quite SN2, not quite SN1, it does a backside attack on the carbon that has more substituents, because as the nucleophile is approaching, the carbon-oxygen bond is already breaking because the oxygen is protonated and has a positive charge. So that carbon-oxygen bond is already beginning to break as the nucleophile comes in. So you have sort of a budding partial positive charge on the carbon that the nucleophile is going to be attacking. And so the carbon that's better able to support that budding partial positive charge will be the more highly substituted carbon. So for example, we could take something like this. Keep it small. Doesn't really need to be big to make our point. So we're going to protonate. So some source of a proton is going to come in, HCl, whatever. And I will protonate the epoxide. So now this is really ready to be attacked by a nucleophile. It's so reactive that I can use something really weak like water or methanol, for example. Let's use methanol. And I'm going to use the lone pairs of electrons on the oxygen, right, to do the attacking. So that's going to be my nucleophile. That's a weak nucleophile, right? It's a neutral molecule. And we're going to create two products here. One of these products is going to result from attacking the carbon on the left. So I could attack that carbon, or I could attack that carbon and crack the ring open, right? If I come in and attack that carbon, then I get and break that bond right there. And anything in the reaction mixture that can take a proton away, probably just excess methanol, anything at all that could act as a base will deprotonate this. And you'll get essentially alcohol and ether functionality on the molecule. If I were to, for example, attack the other carbon, so let me just duplicate this and bring it down here. Now, instead of attacking that carbon, I'm going to attack the other one. So theoretically, that's a possibility. What I get is this. And again, we're going to lose a proton here, so and I get a different regioisomer. One of these is going to be the major product, and the other one is going to be the minor product. The major product is going to come from attacking the more highly substituted carbon. So this right here will be the major product, and this will be the minor product. So why is that? So we're going to take that first step and just expand it a little bit. I'm going to take this, and I'll have it just already protonated. So start out skipping a step here. Okay, so here comes your nucleophile, and it's going to attack the more highly substituted carbon under acidic conditions, right? So under acidic conditions, we have the oxygen protonated. What's going to happen is, draw this in a different color so that it's easier to see. The nucleophile is going to be approaching, but this bond has already started to break. There is a budding partial positive charge on that carbon, and the carbon that is better able to support that partial positive charge, that is the more highly substituted one, is going to be the one that the nucleophile attaches to. So this is why it's not quite SN1-like, right? And it's not quite SN2, because you don't actually make like a bona fide carbocation. This is how we rationalize that regiochemistry. So we end up with the major regioisomer being the one where the nucleophile is attached to the carbon that had more substituents on it, because as we are approaching, as the nucleophile is approaching the protonated epoxide, the bond between the carbon and the oxygen and the epoxide is beginning to break already. It's putting a partial positive charge on that carbon, and the one that is better able to support that partial positive charge will be the one that we find the nucleophile has attached to. So you'll get a little bit of the minor product, but the major product will be a more highly substituted one. And then we can do this reaction under basic or neutral conditions. So because these are so reactive, we don't have to protonate the epoxide. So neutral or basic conditions. Regular old ethers need to be protonated before they can undergo nucleophilic substitution reactions, right? Because they're pretty hardy, and the leaving group would be an alkoxide ion, which is really basic and not a great leaving group. But the ring strain in the three-membered ring of an epoxide allows that epoxide to undergo a nucleophilic substitution reaction without first being protonated. And when a nucleophile attacks an unprotonated epoxide, the reaction is purely SN2. So whereas this is like kind of SN1 slash SN2 like, it's kind of neither, right? Because we don't actually form a carbocation, so it's not purely SN1. It's SN1 sort of SN2 like. Under neutral or basic conditions, it is purely SN2 because we haven't protonated the epoxide first. Your nucleophile is going to attack the less substituted carbon, or the most unhindered, the least sterically hindered carbon, the one that's sort of like got less substituents on it. So we're going to take our molecule again, and we're going to do this under neutral or basic conditions. So if I do this under basic conditions, I can take maybe methoxide. Remember, if you've got a small negatively charged molecules can also act as nucleophiles. In fact, they make great nucleophiles. So this is going to come in and it's going to attack the least hindered carbon. And then you're going to have to either do maybe an acidic workup, or maybe you have some excess methanol floating around in the flask, something that's good for a proton. So, or H plus workup, just to protonate the oxygen. So this is, we say this is under basic conditions because you're starting out with a nucleophile that has a negative charge, right? You have a little base there. And you'll protonate this oxygen, and you get your ether functionality over here. So if you're doing this under neutral or basic conditions, your regioisomer is going to be such that you, whoops, I put the wrong number of hydrogens there. It's going to be such that you have attacked or formed a bond between the nucleophile and the less sterically hindered carbon in the unsymmetrical epoxide. So you'll see that your hydroxyl group will be on the more substituted carbon on the unsymmetrical epoxide. So to recap this, under acidic conditions, so this is for obviously asymmetrical epoxides, the nucleophile, I'll just abbreviate it NU, preferentially attacks the more highly substituted carbon in the ring, and under neutral, so under neutral conditions, we did this under basic conditions as just an example, but if we were doing that under neutral conditions, I would have just used methanol, right? They're so reactive that you can use a crappy nucleophile, like a weak or a neutral nucleophile, like methanol or water or ethanol or something like that. It doesn't have to be the methoxide, ion. So under neutral conditions or basic conditions, the nucleophile preferentially attacks the less substituted or the less sterically hindered carbon. In the epoxide. So that's going to do it for ethers and epoxides. I'm going to save amines for their own video. And when we get to amines, we're basically going to go through just their nomenclature and their physical properties and sort of like a couple of reactions, because we end up using them in our further chapters with our carbonyl compounds. So we'll see a lot of reactions with amines coming up in other chapters. So we'll introduce them and talk about their physical properties and how to classify them and how to name them and all that stuff in the next video.